What's he doing? Whoa, whoa. Yo, is that magic? Nah, bro. That's magnetism. Let's get awkward. Welcome back to Awkward Science. Today we're going to be discussing magnetism by looking at magnets and magnetic fields. So, in your section questions, you are asked the question to explain why the North Pole of a magnet is attracted to the geographic North Pole, yet like poles repel. Well, let's break that question down. First, let's look at that idea of the North Pole of a magnet. What does that mean? Well, all magnets have two poles, a north and a south pole. And you can't isolate them, meaning you can't cut a magnet in half and have a north pole and then a separate south pole. If you cut a magnet in half, you're going to have two smaller magnets, and each one is going to have a north and a south pole. It doesn't matter how small you cut that magnet down, every little piece is going to have a north and a south pole. Okay, let's look at the part about repelling. Well, this should sound familiar because it's a lot like electric charges. Opposites attract and like repels. Except now instead of positive and negative, we're talking about north and south. We don't want to confuse the two things, like north is not positive or negative. They're different. This is magnetism we're talking about now. So kind of the main idea we want to take away is that like things repel and opposites attract. So if you have bar magnets with a north and south pole labeled on them, we know that the poles that match each other are going to push away, and poles that are opposite are going to be attracted to each other. Now we can describe this force the same way we did with electrical forces using a field diagram. Magnetic force works at a distance, kind of like gravity works at a distance, or like we saw with electric charges, meaning it doesn't have to be touching something. So force field diagrams show us how that can happen, how if something is within those fields, it's being acted upon by the magnetic force. Well, notice that where the lines are closest together is where the forces are strongest. And in magnets, that is going to happen at the poles. So the closer you are to the pole, the stronger the magnetic force. When you're further away from the poles, then that force is going to be weaker, and we'll see that the field lines are further away from each other. Now, you can use a compass. So I'm sure you've seen a compass before. It's got a little magnet on it. That's what the needle is a little magnet that is balanced in a way that it can move freely. And the labeled part or the painted part of the needle is going to point from the north to the south along a field line. So basically it's pointing toward south. But that kind of might start seeming confusing. Wait, it's pointing south, but we use a compass to point north. All right, it's getting kind of weird. Well, Earth is also, it's like a big bar magnet. It has a magnetic field. Scientists aren't exactly sure why it has a magnetic field, probably something to do with the liquid metal in the core of Earth, but we're not exactly sure how that creates a magnetic field. That magnetic field has even changed over Earth's history, but what we do know is that it does create a magnetic field. You might notice in the diagram above my head here that the field lines are actually pointing from the South Pole around toward the North Pole, which is the opposite of the field diagrams that you saw in the bar magnet on the previous slide. Normally, in a magnetic field diagram, the field lines are always going to be pointing from north to south. So is this diagram that I'm showing you right now wrong? No, it's right. What's wrong is the way that we have chosen to label the planet over time. See, in fact, the magnetic north pole of Earth is down in the southern hemisphere at Antarctica, at the geographic South Pole. So we have to make the distinction here between magnetic and geographic. Geographic is like what we see on a map. We describe the South Pole on a map as the geographic South Pole. The North Pole in northern Canada is the geographic North Pole. The magnetic poles are the opposite. So the magnetic North Pole is actually down in Antarctica, and the magnetic South Pole is actually in northern Canada. So let's go back to that question that we've been trying to answer this whole time. Explain why the north pole of a magnet is attracted to the geographic North Pole, yet the like poles repel. Well, the magnet in my compass isn't actually like defying the laws of magnetism. It is being attracted toward the magnetic South Pole, which is the geographic North Pole. All right, I know that's confusing, but I hope that helps with your understanding of magnetism. Stay awkward, and we'll be back soon to talk a little bit more about magnetism.